Hi, this is Veder Gouwmans from Software for Chemistry and Materials, and I'll guide you through a few nice features in the Amsterdam Modeling Suite, especially the ADF input. So what we'll do is we'll import a smells structure, use that as a monomer, and then build a trimer from that, generate a number of conformers, calculate its infrared spectrum, and average Boltzmann average over the lowest few conformers. So let's get started. As an example, we'll take dimethyl sulfide, go to the Wikipedia page, look at the smell string, copy that into ADF input, and maybe pre-optimize it a little bit. And then we use this as a monomer in the new polymer builder, which is available on the edit polymer. And we can use a number of default monomers, or we can use our own as we just imported here. We need to define the link points, so point 1A and point 1B. And we want these link points then to be used to create 3 units in a row, like that. There we go, we're done. And now we want to sample conformational space by using the conformer option from the graphical user interface. Take the lowest 600 conformation, do a first check if they're geometrically similar within 0.2 angstrom, and after it's optimized locally with the universal force field, do that again with a slightly tighter criterion. In this case, we're interested in the infrared spectrum, so we don't need to keep the chirality fixed. We save this one as a job file, so conformers DMS3, and run this. It's generating conformers. It shouldn't take too long. When it's done, when the job is finished, we can visualize the conformations by selecting the job in the ADF jobs GUI and selecting movie. Let me drag that over here. And so we'll list the lowest conformers as a function of energy. Let us switch here to kilocalories per mole. I see that there are around 10 conformers which are within 2.5 kilocalories per mole. So we want to use those in our DFTB calculation, re-optimize them, and calculate the frequency. So we use the SDF filter for that. So we switch first from conformers to DFTB. We want to do a geometry optimization followed by frequencies. And as a model, we'll use GFN XTB with parameters for most of the elements in the periodic table. Now, rather than using this input structure, we want to go and select the structures which we've just calculated. So we want to select here the file that has those structures, which is this SDF file, which contains all the conformers. So we now use that as an input, and we can also tell which one of these conformers, which ones we want to include. So let's say we want to include all conformations which are within 2 kilocalories per mole, and once it's done, the re-optimization with DFTB, we want to resort them and also get rid of any duplicates and also realign all the structures. So we save this as conformers DMS3. Now I don't want to replace that as, so append DFTB, save, and run this job. And now graphical user interface will have generated all the necessary input files for you. So there's a file called run all, and all the DFTB jobs will be run one after the other. And let's let that run for a bit, and we'll be back in a second. Okay, so here we are. It's taken about 10 minutes or so to calculate 28 different conformers. Now we can visualize those again by using SCM Movie, and we will see slightly different ordering here of the lowest conformers. So there are 5 conformers which are very similar in energy, and then a couple of more which are about 2 kilocalories per mole higher in energy. Let's switch to kcal per mole again. Okay, now we already calculated the frequencies for each one of these, so we can go straight to SCM spectra, and that will automatically calculate. So these are the individual spectra here. It will automatically calculate a Boltzmann average spectra with a temperature of 300 Kelvin. So since we have almost 30 different conformers, it will take some time. So if you want to do a similar analysis and you want to change, let's say, the weighting, I would suggest you use a smaller number of conformers. But here we are. So this is the Boltzmann averaged infrared spectrum for this trimer here. Let us know if you have any questions on using functionality in the GUI as well as other aspects of the Amsterdam Modeling Suite.